All right, I understand you wanted me to work on one of those problems on the homework set.
Yes.
If I recall correctly, we have a ladder here with a mass of 8 kilograms. We know that there is a chain here, and this is a height, or from the top, 0.5 meters. And then over here, we know the ladder is 1.3 meters tall. It's not the length of the side, which we will need to know later. And uniform distribution, so the center of gravity of the side is halfway up that.
And the bottom was 1 meter.
Pardon? Oh, that's right, thank you. And that's 1 meter.
If we're going like purely off of this, it's 1.1.
Oh, it's 1.1 meters?
Yes.
Okay.
According to the problem, yes. I thought we were simplifying it,
No, I can't read.
but got it.
You can do physics, just not.
Sorry, I never learned how to read. I shouldn't mock that, I was doing an homage to, Wayne's World. It's the Oscar clip. If you haven't seen Wayne's World, I recommend it. All right, so, if we look at the force, we have to look at it actually 2 different ways, so let's just go ahead and get that other thing out of the way. Because the mass of the ladder is 8 kilograms, and it's possible that you might have seen it earlier where I said just half of it was 8 kilograms, but the whole thing is 8 kilograms. If I look at the whole thing, if I do a force diagram of the entire ladder, and I really don't need to write it a 3rd time, what are the forces acting on the entire ladder?
Weight going down, like right in the middle. And then, do we care about the tension going in?
It's an internal force.
So, it doesn't.
I guess when we throw the chain in there, there's a hinge up here. That's all part of one object, so internal forces we're not worried about.
All right then. Normal force on the ground.
And that's it. This is how we get the normal force. So, assuming, well, I know that we'll need it's a 3-dimensional problem. So, y minus w equals 0, because it is in static equilibrium and static rotational equilibrium. Normal force equals the weight, which is mg, which is 8 times, put it on our current Earth, 9.8, some generic spot on our current Earth. Whatever that is. So, 78.4, I think.
You're right.
So the total normal force is 78.4 newtons. Now we got to sort of cut things in half. We have to look at half the ladder. I know that the normal force acting up here is going to be half of that. 39.2 newtons. I have the weight of half of it, which is
Oh, yeah, I see what you're saying. We're looking at the force.
yeah.
Okay.
I know that there's a tension acting this way. And then there's some force acting up here. Now, they assume some generic direction there, but it seems like if the total normal force is this, is equal to the weight, then if I'm looking at half the ladder, I've got half the normal force, half the weight. It still balances out. This can't have any vertical component in the end. This has to be horizontal. This is some, I'm gonna call it Y2. Because basically you're pushing against this bolt at the top of the ladder. It's pushing against it, the bolt's pushing back. I'm making an assumption that the chain has no significant mass.
Indeed, sir.
All right then.
So we're now looking at what is the tension in the rope, or tension in the chain. We have, well, our J equation, they equal each other. Our I equation, let's go ahead and put down the J hat equation. 39.2 minus 39.2 equals 0. Now, if you were not aware of that, congratulations. You now have learned something incredibly spectacular. The I hat equation, we have y2 minus ft is equal to 0. And now the k hat equation. Because we know the normal force, unlike what might have been done on a video that will not be seen, then it's probably best to pick a point of rotation, axis of rotation, for something that doesn't have any natural axis. Some point where there is currently an unknown, which means picking it here or here.
Like you.
Yeah, that's the one that makes sense. So we end up with the total torque. So I have the torque from the tension. And again, if this is my, actually, I might have to change that. If that's my pivot point right there, this tension is trying to rotate it clockwise, which puts my thumb into the board, which is the negative direction, so that's negative. The weight is trying to rotate it also clockwise, minus the torque from the weight. And then we have this torque right here, which is trying to rotate it counterclockwise, which is the positive direction, plus the torque from the normal force equals 0.
Now,
Yes?
When I did my finger maneuver, how did you go, cause if tension is going this way?
All right, so if I push right here, which way is this thing gonna rotate? Yeah,
Oh.
so, into the board. The normal force is pushing up, so that rotates it positive direction. And then weight, I can just let go.
I see.
All right, other questions up to here? All right, so finding torque at a slant, which does relate to the lab as mentioned earlier. I'm just gonna call that Y for right now. This is my pivot point right here. This distance right here, we've already calculated off screen. But if the height, oh, actually, we need to recalculate it because that number changed. So my height is 1.3. The base here, from here to here, is 0.55 meters, and I need to know that length, which I suspect is somewhere a little bit above 1.39.
is that 0.55?
Yes,
Because we're doing,
because that's 1.1 meters,
Just
not
half.
1 meter as previously advertised. And the answer is
1.41. Would you like me to keep going?
no, probably good enough. All right. Is it 1.414?
1.411.
Ah, okay. All right, so the torque from Y2. No, not that one, from Y. I know that my radial vector, or my moment arm, goes from the pivot point to where the force is applied, so R is that vector, Y is up. Or that's my force. And again, this should match what we had before. If I do R cross F, hand points in the direction of the first vector, so my fingers curl the shortest way to the second vector, thumb points out, positive direction. And that's why we have a plus here, another way of looking at that. So the magnitude of this would be RF sine of this angle right here, which I'll label as 5. And that will be 90 degrees plus this angle, which happens to be the same as that angle. If I have any line, if I have parallel lines cut by a transverse, alternate interior angles are congruent. Use some geometry language, or at least back in the day. So that angle right there, which we've already calculated, but we'll do it again for the video. I know that this is, oh, actually, we need to redo that because, again, different number. 1.3 and 0.55, this angle down here, which I will give it a label of, what number? Let's go with beta. I don't think we use beta for anything. So beta is the arctan of 1.3 over 0.55.
Which is 67.07 round degrees.
Thank you very much. So this angle here, well, that's 90 degrees, and this angle right here is 67.09. So my torque from that normal force at the bottom is going to be R, 1.41 meters, times F, which is, we actually know that number, 39.2, times the sine of 157.07 degrees. And that will give us something absolutely magical. Which someone is going to share.
So we added 90 plus 67.07 to get that
Yes,
angle.
still yes.
Got it.
Though I appreciate that is proper grammar. That being an adjective needs something to be describing.
As you can see, my previous grammar is not my friend. But, yeah.
No, you corrected it. I was going to answer it after that, and I should have waited.
Indeed so. On to weight.
So someone's about to tell me what this is actually equal to.
Oh,
Like 21.534.
21.
0.534.
What units be?
newtons meter.
Newtons per meter.
Newton meter degrees.
Did you say per?
No.
All right, so we now have this one. Torque from the weight we can also calculate. Again, very similar to what's been done before. It's going down. The weight is acting at the center of this, so we'll go for the typical stunning visual effect. Ooh. Right, there we go. R is going this way, that's the radial, that's the moment arm for the weight torque from the weight. And that is incorrect because apparently I can't go without making mistakes. That direction. We changed pivot points. I should probably adjust. So my weight is going down, R is going this way. need to figure out that angle there.
We do, I guess, adjacent. It's not tangent.
Okay,
So I think it's gonna be sine.
oh, we're still going with sine, we just need the angle. All right, let's think about it this way, I know this angle here is 67.07 degrees. That's 90 degrees, what is this angle right here?
6707.
Oh, we just do, 90 minus 67.07?
Yeah, that's the process. So 22.93. So the torque from the weight would be the distance, the length of R from here to here, which is just half the total length. So that would be 0.705 meters. Times the force of that half, so 39.2 newtons, times the sine of 22.93 degrees. And someone's about to reveal that answer.
705, and that came from,
That is the distance from the center of mass to the top point. It's half of the total length.
yeah. So we took 1.41 divided by 2.
Yep, and that's what I got. And the answer is 10.767. All right. So we now know two of these torques. The last one remaining will tell us the tension in the chain.
Could we not just move the tension, the one we don't know, over the other side, make it positive, and then just add the other two up?
Sure, we can do it that way. More than one way. It's, that'll help tell us the torque, that won't tell us the tension.
Yeah,
So, okay,
I was just looking at the T, I guess I said.
All right, so the torque from the tension, bringing that over, would be the torque from the normal force on the ground, minus the torque from the weight. And the torque from the normal force on the ground was the 21.534 Newton meters, minus the torque from the weight, which was 10.7671. And that equals 10.7. Oh, it's going to 10.767. I think so.
10.7669, which is 10.767.
All right, so now here, again, this is our pivot point. R is the vector that's that long, so we need to figure that out. So let's figure that out. I've got that unknown length there. I don't know how far it is that way, but actually I do know that's 0.5 meters. I know that. I'm trying to find this. And I have one other piece of information that we've already solved. This angle, I know, is 67.07 degrees. How do I find the hypotenuse?
So, 0.5 sine 67.07.
No. That, you see a ballpark, you're not there yet. It is sine we're gonna be working with, however, what you gave us would be as if 0.5 with the hypotenuse.
Cosine, or no, not cosine, sine 67.07 divided by 0.5. No, again. Or would it be equals 0.5?
Why do we call that R?
Or
Sine of 67.07 degrees is equal to the opposite divided by the hypotenuse. So R is 0.5 divided by sine of 67.07 degrees.
so close.
And so R is presumably, as usual, something just absolutely magical that will make us all better as human beings.
And 0.5 for. let's see how we can get
0.54,
that. 28992.
0.543. All right,
And so now we have the 0.543. We have the unknown f and the sine 67.07.
all right. So my radial vector is that way. My force is that way. I need to find that angle. Well, I know this angle here. That was done already. That was the
0.93.
I know that is a right angle. So this torque from the tension is going to be equal to R, which we just found, 0.543 meters, times the tension, times the sine of
112.97.